All right. Well, thank you all for joining us again for the March DGC seminar. I'm really glad that we're able to continue this monthly seminar series at this current time. But anyway, today we have Professor Daisuke Nagai from Yale University to come to tell us his ongoing work in trying to constrain the universe based on large-scale computer simulations. Just a very brief intro for Daisuke's academic history. He actually graduated from the University of Chicago in 2005, working with Andrei Kravtsov and John Karlstrom. At the time, we just missed each other by a few months. He was immediately awarded a prestigious postdoctoral fellowship at Caltech and stayed there until 2008 before he joined Yale faculty. Today, without further ado, I'm really very much looking forward to hearing his latest work on CAMELS. So Daisuke, please go ahead.
Great. Well, thank you very much, Xiaowen, and thank you for the invitation to join this seminar. I'm very excited about sharing some of the things that I've been excited about, I've been working on. The way I'm going to structure this is I'm going to start my background in cluster cosmology and astrophysics. So I'm going to start from the large scale of galaxy clusters, going down to galaxy groups, and then going down to smaller scale of diffuse medium in circumgalactic medium at the end, where CAMELS work has really made big changes and advances. So I hope that I will structure in that way. And I would like to start with this, let me see. This picture this in the backdrop of the cosmology, I think we've seen remarkable advances in our understanding of the universe from CMB to large-scale structure. And we have this beautiful standard model of lambda CDM, which consists of things that we don't really know much about. And I would like to argue in this talk that diffuse gas in cosmic ecosystem, DGCE, which is the main theme of this working group, really hold the key for advancing our understanding of galaxy astrophysics, as well as also precision cosmology in the future, and see if I can actually make that case. And there's a lot of exciting development that will likely happen over the next decade. So here's a landscape of sort of exciting development on the observational front, all from microwave to radio to galaxy surveys, all the way up to X-ray. And we're really entering into the golden age of multi-wavelength surveys, which allows us to map the distributions of dark matter, gas, and stars in exquisite detail. And one of the sort of newcomers here is this diffuse gas in cosmic ecosystem, which has been elusive. Those used to be known as missing baryons. But now that we actually can have access to detecting them, and now we are also in the position to be able to characterize them, that understanding this is sort of like the last missing components. And detailed characterization of this will help maximize the scientific returns of all of these surveys. And here, sort of in this sort of new era of data-driven large astronomical surveys, we're moving from sort of taking census of baryons to precision modeling of baryons, and that those 4% or 4 to 5% of ordinary matter, which are mostly made of this diffuse gas in cosmic ecosystem, actually plays a significant role. They are the beacon for us to be able to detect and probe large-scale structures in the region that has been very difficult to see. I think we have a lot, and then that for precision modeling at the level of 1% on various scales from large to small scale really requires detailed understanding of those baryons. I'll start with this status of sort of studying diffuse gas in galaxy clusters, some of which has actually been pioneered by, for example, using CMB as a backlight through this Sinyov-Zeldovich effect, which is an inverse Compton scattering of CMB photon. When it traverses through hot electrons in galaxy clusters, it leaves a unique imprint on the CMB spectrum, which allows us to detect galaxy clusters out to arbitrarily large redshift. And recent development from this survey from ACT, Planck, SPT, they have been detecting hundreds and thousands of massive galaxy cluster above 2 times 10 to the 14 solar masses, which enabled us to actually place interesting cosmological constraints in the future of the CMB surveys based on Simon Observatory and CMB-S4. They are promising to tighten the cosmological constraint of things like the equation of state of dark energy, neutrino mass. When it's combined with the galaxy survey, you can get redshift, and you can really put interesting, unique constraints from the future surveys. However, one of the most important sort of systematic uncertainties actually lie in astrophysics of galaxy clusters, and detailed understanding of this diffuse gas in galaxy cluster known as the X-ray emitting intracluster medium is one of the major sources of systematic uncertainty before we can use the statistical power or full statistical power of those future surveys. Another exciting development is actually in X-ray. This is the compilation from eROSITA, Russian-German mission, which has been really pushing the frontier of mass limit from galaxy clusters all the way down to galaxy groups. You can see this black dotted line, which are the galaxy groups detected in early eROSITA data called EFEDS. And they are detecting the galaxy groups down to 10 to the 13 solar masses in nearby universes. And as you go down up to higher redshift, because of cosmological dimming, the X-ray sources become a little bit dimmer. So you see that this selection function, which you start to see more massive object. But in low redshift universe, you can see the diffuse gas within galaxy groups. And more recent, more updated version of ER1, ERAS-1 data has been used to place things like cosmological constraints. Here again, that the astrophysics of diffuse gaseous medium in galaxy groups is one of the major sources of systematic uncertainty in sort of pushing this technique forward into the future. Perhaps even further, using the same eROSITA data, you can actually dig deeper into the signal to detect warm, hot phases of gas around galaxies. And the way to do this is to combine the eROSITA data with galaxy surveys. And knowing where the galaxies are, you can stack the X-ray pixels in eROSITA sky and detect the warm, hot phases around galaxies known as the circumgalactic medium. And there has been exciting detection of the X-ray emission from low mass galaxy, star-forming galaxy, quiescent galaxy. Depending on the galaxy properties, you can stack different types of galaxies, and you can actually get detection of the X-ray emission profile of the nearby galaxies. What's interesting here is that the measurements are actually rather quite exquisite. That some of the models of the cosmological simulation models from Eagle, TNG, SIMBA, they actually some of the measurements actually there's some tension between observations and simulation predictions, which I will get to in more detail using CAMELS simulation later. Perhaps equally important is the use of galaxy and lensing survey. The diffuse gaseous medium actually has a significant impact on our ability to do cosmology using lensing survey, known as a cosmic shear. This is one of the primary science goals for something like Euclid, which has been launched recently. And that the main source of systematic uncertainty, well, one of the main sources, but more of a theoretical uncertainty, lies in how baryonic effects on this thing called matter-power spectrum. So what's shown here is the effect of baryons on the matter-power spectrum. You're looking at the effect of matter-power spectrum in simulation that has hydrodynamic effect compared to the same simulation that doesn't have any galaxy formation physics. And prediction is that the effect of baryons are potentially very significant as a function of scale. from large scale to small scale, and the effects are especially large on small scale where galaxy formation physics has a significant impact. So some of the simulations, like original illustrious simulations, had the significant blowout of the gas, which led to significant spread of the baryons, compared to simulation that doesn't have any AGN or actually predict significant cooling, which leads to significant excess power. And then the more realistic, more modern realistic simulation that has the moderate feedback and self-regulation due to AGN, they fall somewhere in between. Nonetheless, even among some of the simulation that seems to reproduce the stellar properties of present-day galaxy, seems to predict a different amount of baryonic effect and baryon spread, which is basically as a source of significant systematic uncertainty at the level of tens of percent on certain scale. And of course, it becomes slightly smaller as you go down to larger scale. But a lot of the information from the Euclid and future galaxy surveys are really lies in exploiting those small scale signals that we expect to get. In the future, we really need to get this model and understand this baryonic effect at the level of a few percent in order for us to be able to then do interesting cosmology. So here's another area where diffuse medium, which are most of the baryonic effects are actually the key for doing cosmology with galaxy survey and lensing survey as well. In terms of what we have understood about baryonic effect, the baryonic effect have an impact on stellar fraction in galaxy clusters to groups all the way down to galaxies. And without the strong AGN feedback, it is widely known that this AGN feedback it will likely play a significant role in massive galaxy clusters, galaxy groups, possibly all the way down to Milky Way size object. This is the results, the models that doesn't include any AGN feedback, and by including the significant AGN feedback that regulates the star formation, otherwise you get overcooling problem. You can then reproduce the observed stellar masses in those massive halos. On the low mass end, on the other hand, is thought to be regulated by the supernova feedback, although there are some interesting questions as to whether the AGN might even play a role in dwarf galaxies. Maybe I'll put just a little bit of question mark as to what extent we can really make that clear dichotomy between the star formations, supernova, and AGN feedback in this kind of way. But this is sort of our current canonical understanding. On most of the massive end, the AGN is known to have a dominant effect. We do have a pretty good observational evidence of the AGN feedback playing a major role in regulating the cooling in galaxy clusters. What's shown on the left-hand side really shows the AGN bubbles and jets that are regulating cooling in the center of galaxy clusters, and there are many examples of this. But some of these X-ray bubbles or X-ray cavities and radio bubbles has also been seen in galaxy groups. These require significant more observational time, but there has been many detections of X-ray cavities and radio bubbles also seen in galaxy groups as well. I think one of the interesting the plot is this strong correlation that exists between the power in the X-ray cavity or radio bubbles, and there seems to be just enough energy in those radio bubble in the form of possibly the high energy thermal particles or possibly cosmic ray that have enough energy to actually offset cooling. So this strong correlation between the cavity power and cooling is one of the interesting evidence on macroscopic scale that maybe there's some kind of self-regulation is happening due to AGN feedback offsetting cooling in massive clusters. The AGN feedback also have a big effect on the total baryon budget, especially the diffuse gas fraction. And this is the latest state-of-the-art observation of gas fractions in clusters to groups. Because galaxy groups have smaller potential, the AGN feedback tends to have a much bigger effect, which pushes out the gas, and you expect to see the lower gas fraction. And this is the latest results from Chandra and XMM, which shows a clear mass dependence of gas fraction evacuating gas in galaxy groups And it's widely believed that this is probably due to some impact of significant aging and feedback playing an outsized role in galaxy groups. On the cosmological simulation side, there has been a number of simulations from the large flagship zoom-in simulation shown on the left-hand side. There are many of, and that there are also the zoom-in galaxy cluster simulations, and there are also a number of. And most of those cosmological simulations have sort of a key ingredients for feeding supermassive black holes and how energies are released and heat the gas in the surrounding diffuse gaseous environment. In galaxy cluster, you see most of those baryons as well as stars. So the galaxy groups and clusters are excellent laboratory for really just understanding the detailed feedback mechanisms that are playing a role in shaping the properties of diffuse gas in halos. Just briefly about how feedback, the AGN feedback is actually implemented. First of all, it starts with the feeding. Most of the cosmological simulation uses Bondi accretion as a sort of simple prescription for feeding black holes. It comes with a number of caveats. It assumes spherical symmetry, which might not necessarily hold in terms of the actual accretion physics. And then this, of course, feeding requires, the self-consistent modeling of feeding really requires 14 orders of magnitude in scale in order to go all the way from the kiloparsec macroscope scale all the way down to Schwarzschild radius onto the accretion regions. Equally important is actually the feedback mechanism, which also requires at least 9 orders of magnitude in order to be able to capture how this feedback cycle actually regulates the black hole accretions and feedback. So that's one of the most significant challenges in cosmological simulation has to do with really leveraging those scales, which are very difficult to capture in single simulations. In terms of feedback, most of the cosmological simulation implements sort of 2 major modes of feedback: quasar mode, which is due to the radiatively efficient feedback, which creates the wind and heats the gas, especially significant at high redshift. And there is a radio mode. Many of the cosmological simulation include both of these modes, and radio mode is also known as a jet or maintenance mode, which plays a role in regulating cooling, usually at the low redshift. So here is the status of the gas fraction observation, which I showed earlier, and how that compares to simulations that varies feedback. The main takeaway is that if you don't have too much feedback, these are Cosmo OWL simulation with no cooling, no feedback, you get most of the baryons without cooling. But as you include cooling and star formation, you get what's on the bottom in magenta here. And then that once you add AGN, you can then start to self-regulate the cooling and star formation, and then you get the gas fraction somewhere in the middle, depending on the strength of the feedback. So this is how we come to know that the AGN is sort of required in cosmological simulation in order to avoid overcooling, and also to regulate the overproduction of stars. And this is sort of a slightly more modern comparison. I will call your attention to 2 simulations. One is this red one with the Eagle reference simulation, and also this magenta one with the original Illustris simulation. These simulations were designed to reproduce the stellar mass-halo mass relations in the local universe, as well as the M-sigma relations. So they are calibrated to reproduce stellar properties and black hole properties to be reasonable in cosmological simulations, yet they make very different prediction for the gas fraction. In some cases, you get too much gas, and in some cases, you evacuate the gas too much. The more modern simulation so the Eagle DT9, one soon realizes that when you look at the diffuse gas in galaxy groups, that these simulations seems to be not to be inconsistent with the X-ray observation. So the refinements has been made in order to reproduce the observed stellar gas fraction. Some refinements that has been made are on the feedback models. to make sure that the gas is not cooling too much and that they're not overproducing stars. So the more modern simulation, for example, Fable and Simba, or even Bahama simulation is an interesting one because they didn't really calibrate their subgrid model to stellar physics. They actually used the gas fraction to calibrate their model. So of course, the gas fraction is well reproduced. More modern simulation with Fable and Simba, they also use gas fraction in addition to stellar mass, halo mass, stellar properties, and they're actually doing a better job in reproducing gas fraction, sort of by design. This is an important dichotomy between how simulations are making prediction and then what observations are being used in order to reproduce observations. So there's a very intricate interplay between simulations and observation that are really driving this field forward. And you looking at the diffuse gas in galaxy groups and clusters has been the basic test bed for really improving the subgrid physics in cosmological simulations. In terms of how the questions about how aging and feedback actually work, this is a beautiful observation from Chandra on the shocks and bubbles seen in Perseus clusters. And it's clear that there are jets which drive turbulence, which might sometimes actually inflate radio bubble that are emitting in radios. So it's a very complex phenomena, some of the processes has not really been fully captured in cosmological simulations. So idealized simulations is really the method of choice for understanding the physics of how the feedback actually happens. And there are many different types of models out there, ranging from the shock heating through the radial jets. Some of the models actually creates buoyant rising bubble, which heats the gas, do the PDB work on the surrounding medium and heats the gas that way. Sometimes the jet creates a sound wave. So there are many different types of models, but sort of recent interest has been the exploring the effect of cosmic ray. And I think this type of work, I think, is particularly illuminating. This is a work from Yan et al. And they systematically inject kinetic jets at the top. But then you also turn the kinetic jets into then cosmic ray bubble, and then you also include cosmic ray streaming. The cosmic ray plays a significant role in changing the morphology. For example, the strong kinetic jet creates this very elongated, not even a bubble, it's really just kind of elongated morphology. And they usually create shocks and they run very quickly. They're supersonic shock, which heats the ICM through the shock heating. While if you actually inject energy in the form of cosmic ray, then it actually tends to create slightly more radial bubble-like thing, which we observe in Perseus clusters. And then it actually also slows down the bubble. In fact, some of the bubbles are actually become subsonic if the energies are injected in the form of a cosmic ray. Cosmic ray also do streaming because they're fast-moving particle that if you actually include the streaming effect, it also makes that bubble even slower, more expanded, and they actually create more observed-looking radial inflated bubble. So that's an interesting phenomenon that usually has not been captured in cosmological simulations, but nonetheless, there has been new explorations of how cosmic ray might actually be able to reproduce the observed properties of radial bubble that has been seen in real clusters. Another interesting observation is actually high resolution SZ imaging of radial bubble, which has been taken. There's only one, and that's been taken by Karma interferometer, and these are the prediction of the simulation with a thermal bubble, and this is a cosmic ray inflated bubble. Cosmic rays are very inefficient basically cosmic ray evacuates the thermal gas, and that they are very inefficient in interacting with CMB photon. So in cosmic ray inflated bubble, you see hole in the SZ map. And in fact, that hole has actually been detected in this radio bubble around MS0735, which is very interesting that this actually puts the lower limit on the energy of the cosmic ray electrons. Their electron populations are suprathermal with the 800 kilo electron volts or above, or possibly they are cosmic ray. So there's a very interesting case to be made about the cosmic ray might actually be playing a significant role in doing the heating of the AGN in galaxy clusters. Now, this cosmic ray bubble idea is also very interesting in light of recent observations of less than expected gas motion in CRISM data from the Japanese US mission. That many of those CRISM observations of Perseus and actually now a few more clusters are consistently observing a gas motion that are of order 100 kilometer per second, unlike several hundred kilometer per second that has been expected, or sometimes in some cases thousands of kilometers per second if that's in the case of thermal jets. It seems that this cosmic ray bubble, which tends to slow down the gas motions due to the creation of buoyantly rising bubble, maybe that we might be seeing some effect of that consequence of cosmic ray bubble in the form of CRISM data. This remains to be seen, a very exciting topic in the future. So I just wanted to sort of start with this galaxy clusters because you can see the AGN feedback up close in detail, and you can even sort of gain some insights into the physics of AGN feedback by looking at these radio bubble in clusters. But I would like to switch the gear to smaller masses in and around galaxies, and these are the circumgalactic medium. These are the diffuse gas, which has only been, I think, until really recently, detected through the absorption line studies of background quasars using HST, and that really pioneered and has been pioneering our ability to understand these diffuse gas properties around galaxies. But I think the future of this field is particularly promising because of this new observation, and multiple probes will become available, including SZ effect that I talked about, as the CMBS4 and Simon Observatory, as they improve sensitivity and do this stacking measurements of this very large CMB surveys. One can dig the detection of the hot diffuse gas all the way down to probably around 10 to 12 solar masses, perhaps even more. And because the SZ effect is independent redshift, that you can detect all of these diffuse gas out to high redshift. And as we also discussed, the stacking X-ray signal would also allow us to dig even further, and that there has been exciting recent detection of the warm hot phases of gas in the nearby universe, which I will talk a little bit more about. And of course, absorption line studies has been doing those detections and characterizations in detail over the past decade with the HST costs. And then perhaps a newcomer to this is the fast radio burst, whose detection rate is increasing exponentially with the CHIME and many other versions of FRB probes. And that's actually an interesting new probe that will allow us to also study the CGM in different ways, so that this having a multiple observational probe really allow us to then unlock and study the detailed properties of those diffuse gas in different size halo, all the way from cluster groups down to galaxies. And at the same time, on the theoretical front, and many of the developer are actually also here in this audience, that the new generation of cosmological simulation, which is known as CAMELS, Cosmology and Astrophysics with Machine Learning Simulation, is changing the way that the simulations are done and used to do cosmology and galaxy astrophysics. And what's really novel about this technique, this simulation, which is that at the Simons Foundation, is that now one can actually do systematic exploration instead of doing one flagship simulation of big cosmological simulation. That this new CAMEL simulation is capable of doing several thousand simulation, 2,000 simulation per box of the same box, varying the cosmological astrophysical parameter in the, one at a time, and one can study how cosmology and astrophysics parameter affect the diffuse gas. So this is a simulation from the CAMELS collaboration, which shows the distributions of the density in blue and temperature in red. And you can see that the different subgrid physics from illustrious TNG, SIMBA, ASTRID, and magneticum is doing this feedback physics from supernova and AGN in a rather very different way. Most of those simulations are tuned to reproduce the correct galaxy properties at redshift of 0, but nonetheless, the impact of baryonic feedback on the diffuse gas is vastly different. So with this, the CAMEL simulation, one can then make this observable. Like this is example of X-ray emission in color and properties of galaxies in red cross. And from these simulations, one can create the mock observations of galaxies or the diffuse gas as a function of cosmology. This is a sigma 8 parameter, just as an example, as a function of supernova feedback energy, as a function of AGN feedback energy, and how each of those physical processes or cosmological parameter impact the observables. So this is sort of a new era where we can emulate the multi-wavelength surveys or even directly observable as a function of cosmology and galaxy astrophysics. So equipped with this CAMEL simulations and our ability to emulate the different kinds of observable, we took this measurement from the ERAS, the stacked X-ray measurement that I talked about earlier from EROSITA collaboration from ERAS-1 data. This is ERAS-4 data from Jan et al. The measurements are exquisite and very interesting. And I'm showing just a handful of parameter, the supernova 1, AGN 1 parameter, omega matter sigma 8. And the color-coded regions are the prediction of X-ray surface brightness profile in soft band, 0.5 to 2 keV as a function of radius, projected radius. And you can see these are the Milky Way size object, 2 times the Milky Way M31 size, and even more massive objects. And here you're varying the parameter, supernova 1 parameter, relative to the reference model, which is tuned to be 1. And as you increase the supernova 1 parameter, it actually increases the X-ray surface brightness. Interestingly, the AGN1 parameter has very little effect in this particular parameter space. And this is TNG models in CAMEL simulations. Point is that you can vary the feedback strength in supernova AGN. We've done the same for supernova 2 and different supernova and AGN parameter. And you can always find a model that matches the observations. One can do this for TNG model, SIMBA model, and ASTRID model. And you can always find the model that reproduces, for example, luminosity stellar mass relation, because we're exploring fairly broad range of parameter space, and we can always find the model that fits the data. I think what's interesting to ask at that point is that once you reproduce the best fit model, once you get that best fit model from each of the subgrid physics, ask a question: what does the stellar property actually look like? So then this is the stellar mass fraction, stellar mass halo mass ratio as a function of halo mass. And that this dotted line is the observed stellar mass halo mass relation, which we should reproduce if we have the right galaxy properties. And what we find is that the best fit model seems to favor rather strong feedback in all of those subgrid physics. And then as a result, because the EROSITA data favors stronger feedback model, that it has a tendency of predicting the less stellar mass there are around the Milky Way size object. So stellar mass, so there's a tension between X-ray observable and stellar properties. There's no model that we've looked at so far that can reproduce both hot diffuse gas and stellar properties at the same time. So that's interesting tension. Of course, maybe that indicates that there are some systematic uncertainties in these measurements. So, if the measurements, the actual measurement of CGM is actually a little bit higher, or somehow we over subtracted the foreground and background signal, that might actually impact this. Interesting way forward is that one can actually do a similar exercise using stacked SZ measurements, use the same galaxy catalog, stack, for example, ACT data, and then get the consistent, we can do the similar analysis using CMB data, which has a very different systematic. So this is something this is for the future work that we're currently working on to see if this tension really still exists for multiple data sets. The other things that we find interesting is that this is a work where we try to quantify the feedback energetics in CAMELS simulations, in particular TNG and SIMBA, which seems to have a very different types of feedback. And here, by changing supernova 1 parameter, this is the stellar feedback efficiency for any given star formation rate. The changing this supernova feedback efficiency doesn't seem to actually have very much impact on the feedback energy of supernova too much. But somehow this is actually regulating the accretion rate onto the black hole, which changes then in turn has the impact on the amount of thermal energy that are injected by AGN. So this is an interesting coupling that we didn't really know about, that the changing the supernova parameter changes accretion rate onto the black hole, and therefore the amount of energy that get injected in the thermal form. So that was an interesting, intricate interplay between supernova and AGN in this particular model, the TNG model. On the other hand, in the SIMBA, when you actually change the supernova parameter, as you increase the supernova, the supernova energy is much higher, and vice versa, so that you see the very different trend and different coupling between supernova and AGN. This is an interesting relationship that really needs to be taken into account when we start thinking about how to model the impact of the feedback on baryon cycles. Different subgrid physics treats the impact of feedback in a very different way, and supernova and AGN feedback interact very differently. So that some of this would have to be then captured into another sort of interesting avenue is to look at the analytical models of CGM, and there are a number of models that has been out there. And so we have been conducting the comparison of various models that are based on different types of assumption: precipitation model, isentropic model, cooling flow model, baryon pasting model. They make very different assumptions about the state of diffuse gas and focuses on different aspects of CGM. There are some agreement and there are some significant disagreement. It's just really big, depending on the assumption that one makes in these models. And the hope is that we can use something like a CAMEL simulations to test some of these assumptions, possibly rule out, really in the process to hopefully learn how to actually improve the analytical models and also capture the essence of what is most important. What are the assumptions that are playing an underlying role in shaping the CGM properties? So maybe I'll end this talk by some of one of the topic that we are very excited about in our research group, which is the prospect of using fast radio burst as a cosmological and also galaxy formation physics probe. And this has to do with using FRB as a beacon, and the FRB signal, as they traverse through, it creates this, basically they're sensitive to dispersion measure, the integral of electron density along line of sight. Particularly interesting for astrophysics and cosmological application is this component. Of course, the dispersion measure gets contribution from our own Milky Way, its own galaxy host, and then that intervening diffuse gas in IgM as well as CGM. I'm going to focus on DM cosmic, just these two parts in the middle, hoping that we can model Milky Way and host separately using localized FRBs. And that this DM cosmic, if you plot this as a function of redshift, we expect this DM cosmic to increase because you have a lot more sightline through the cosmic time. So you expect to see some kind of relationship, monotonically increasing relationship between DM cosmic and FRB redshift. Particularly interesting is also thinking about this dispersion around this DM redshift, or it's also known as the McCourt relation. And that the dispersion actually contains a lot of information about the amount of feedback and possibly about the strength of the feedback operating on IgM and CGM. So one of my students, Isa Medlock, she has taken the CAMELS simulations and created the dispersion measure map, projected electron density map for SIMBA, TNG, and Astrid. And there are many more models, but we are starting with those three. And as you can see that in the SIMBA, the dispersion measure is a little bit fluffier, more puffed up, a little bit more homogeneous. Well, they're not homogeneous, but they are a little bit puffed up, while Astrid model, on the other hand, has like a very distinct feature, and that there's a clear void, and then there's also the very clustered region. Because of the ejective nature of feedback in SIMBA model, that gas is a little bit more puffed up, and that it's a slightly more uniform overall compared, for example, to TNG and Astrid. One can see this, quantify how the dispersion measure property will look like as a function of projected radius around, say, 300 most massive halo that was indicated in red color. So we identify 300 most massive halos in these simulations. And then we're around each of the center of each halo, we're measuring the dispersion measure profile as a function of the impact parameter around these galaxies or around these halo. And these are the dispersion measure profile for SIMBA, TNG, Astrid, and what's shown here is the background IgM contribution. So there's a clear excess of the dispersion measure, and we're plotting this as a function of halo mass, or color coded as a function of halo mass. And there's a sort of interesting dispersion measure mass dependence that's very clear in Astrid model that are slightly less clear in some other models. And this is a median profile of dispersion measure profile as a function of projected radius around those halos. And there's a clear excess of dispersion measure around due to CGM. And usually the excess is more pronounced in Astrid model above this IgM contribution. This is the upper limit of the Milky Way at the time. I think they're coming down. And so the Astrid model has this more pronounced dispersion measure in the center, while the SIMBA model, due to the sort of the puffed up nature due to effective feedback, that dispersion measure amplitude is slightly lower. And this is in the different halo mass, high mass and low halo mass range. One can also look at the probability distribution of that map, and that the median dispersion measure is roughly comparable in all of those simulations, but the spread of the dispersion measure is quite different. In the SIMBA model, the spread is a little bit narrower, and then in the Astrid model, it's more significant, especially on massive N, because the halo is very concentrated, creating very large dispersion measure in the center. And then so this is the properties of so-called F parameters, measuring the sort of the dispersion of the DM cosmic in the McCourt relation. And this is very sensitive to the feedback physics. This particular parameter called F parameter is reduced when the supernova feedback is very strong. They eject the feedback, and they tend to homogenize the universe. So the F parameter tends to be somewhat low when you have a very strong feedback. And then the Astrid and SIMBA, the F parameter is relatively high when the universe is actually a little bit clumpier. What's shown on this dashed line is the lower limit from the 78 FRBs with a 21 redshift from the Baptista et al. This is a lower limit based on the data that was taken at the time of 2023, which is sort of challenging the prediction from the SIMBA model, though it's not ruling out the model completely. There are some parameter space in which that the SIMBA model still is consistent with that data. But this is the kind of analysis that will help us probe the strength of the feedback, and that the current data is sort of putting the upper limit on the amount of feedback that can operate in CGM and IGM. And also interesting is actually the work done by Matt Gebhardt, who's here on the audience, who looked at the CAMELS simulation, and he showed that the impact of baryons of matter power spectrum, important for the lensing cosmology, is in fact sensitive to this baryon spread, the amount of how the baryons are spread relative to the original dark matter location, and that if you can measure the amount of baryon spread, which is possible in simulation, one should be able to then model the baryonic effect. And of course, the baryon spread is measurable in simulation, but it's difficult to observe in reality. And in our recent work, with also led by Isa Medlock, but also with Danielle and Matt, we found that this F parameter, which is observable from the FRB, it actually correlates very strongly with the amount of baryon spread. So here are the results of SIMBA simulation, which shows significant spread, while Astrid showed probably the least amount of spread. But then that level of spread correlates very strongly with the F parameter, which is sort of also the measure of spread. This is observable. This was not observable. An interesting thing about this relation is that there are this includes simulation with different cosmology, different feedback physics. They all line the same curve. So that the existence of these relations and this relation actually is thought to be insensitive to the detail of subgrid physics. So if we can actually focus on this particular relation, if you can use FRB to measure F parameter, and then that we can infer the baryon spread for our own universe, one should be able to then correct for the baryonic effect on the matter power spectrum. So this opens up a possibility for doing precision cosmology using FRB as a way of really measuring the amount of feedback and baryon spread, and therefore we can correct for the astrophysical uncertainty. And maybe I'll stop here. That one of the new frontier that are emerging in the era of multi-wavelength survey is this precision modeling of DGCE, the diffuse gas in cosmic ecosystem, all the way from clusters to groups, all the way down to galaxies in CGM, and something like a new CAMELS simulation, which is capable of modeling the observable universe as a function of cosmology and astrophysics, is promising for us to be able to then forward model and hopefully doing the precision modeling in the future. So maybe I'll stop here and I'll take any question. Thank you for your attention.
Thank you. Thank you for a very extensive discussion. It covers a lot of work. So we have time for a few questions after the clapping is done. Maybe just to motivate questions. Just a quick clarification question. In one of the early slides, when you show the stacking signal from E Rosetta, it looks to me the difference between star-forming halos and evolved halos. The strongest signal in the 2D image looks almost like unresolved. But then in the spatial profile, in the 1D spatial profile here, it looks quite extensive. Is it just because of the contrast here? And
Yeah.
my scientific question is really, I remember a couple years ago, there's some discussion about contribution from satellite galaxies within these cluster environment. How is that taken into account here?
These are all excellent questions. First of all, I think what we're seeing here is that 200 arc second across. The beam is of order 15 arc seconds. So yes, I mean this first of all, there's a contrast issue. This is a little bit more diffuse, and yes, they are resolved. And that it is showing the angular extents all the way down to 200 arc second, which are resolved with about typically 10 PSF. So yeah, they are resolved, and the results are also the model that are fit to this data, and the angular resolution of, I believe that the Eurosita is of order 15 arc seconds. So there are some issues. In terms of systematics, X-ray binary and AGNs are the dominant systematic, which has been modeled here. So AGN plus XRB, there's some uncertainty, including satellite. Those are the models, and that there are fairly significant uncertainty. So it's still, we should probably take this with a little bit of a grain of salt. But nonetheless, this is the best effort that's been made by the Rosita collaboration. There's also a little bit of concerns about the projection effect of the background groups, which could also contribute. So yes, that's the modeling so this is, you can sort of see that these are the point spread function. These are point sources, and you can see that most of the signal in the center are dominated by the AGN XRB. And
I
then
see.
the outer parts, these are very faint outer parts that are probably difficult to see in the map. Those are the evidence for the idea. Idea is that these are the possible contributions from the extended CGM.
Okay, got it. Thank you. Nastasha?
Hi. So if I'm understanding correctly, one of the things that I'm hearing, especially from the latter part of your talk, is sort of seeing this baryon extent, baryon fraction parameter sort of being this key driver for CGM observables. Well, okay. I started with CGM, so I call everything from Milky Way master clusters CGM. But so first of all, I've heard Reza talk about a similar concept in terms of closure radius, and another one to throw on the pile. And I kind of want to just shamelessly throw in something from my own work, which is with a very much smaller set of simulations in an analytical model, so a couple of fire models, but it seemed that that baryon fraction times metallicity in this case was also a very good way of explaining neon 8 column density. So actually some of these absorption line probes, if you're going to some of the ones more sensitive to the volume filling gas and these things, can also go on the list.
Absolutely. Yeah, I think I just have a one-liner here that similar relation holds for baryon fraction enclosed, but there are multiple versions of this that could be explored. I think this really opens up the area that what are the best sort of potentially useful observable, and there will be a variety of exploration that I hope that will take place in the field to come up with a way to measure this idea of amount of spread of baryons, how they're displaced from dark matter, because that's sort of the one major source of uncertainties in what baryons are doing. And for precision cosmology, that sort of is the key here, that we can see baryon, we can't see the effects on dark matter, but we can at least see baryons. I think it'd be interesting to see baryon fraction, various combination of observable from SZ, absorption line, X-rays, metallicities. I mean, I think once you have the like big list of the observable, I think it'll be interesting to even ask a question that what combination of the observable will give us the maximum amount of information. So I think that's kind of research that I feel that maybe this community can embark on. Each of us who have expertise in different waveband of different observable, we should come together to see if we can come up with the best approaches for understanding baryonic feedback.
I absolutely love that. That was a key point in a lot of my postdoc applications last year.
Yes, so excited.
So yeah, anyway, generally positive vibes. Love the let's get the key parameters down.
Yes.
Thank you. Other questions? We have a couple more minutes. I wonder if I could take the advantage of running the seminar. Maybe just one more follow-up question. Going back where you showed the contrast, the tension between the X-ray luminosity and the stellar mass lag of the production of stars.
Right.
So the data, I mean, the points here are data. Do I understand that correctly? No, on
Point.
the left, the
Yeah,
profile.
that's right.
So, but the different curves are, the data seem to anchor at the blue end. That means lower X-ray luminosity.
Yes. So here, this is a little bit of a deceptive plot where we are showing how changing one parameter, like supernova one parameter, while fixing everything else the same, how that changes the X-ray luminosity. So, but when we do the actual inference, we need to let all of the parameter free. So there are significant degeneracy between supernova one parameter with AGN parameter, cosmological parameter. This is the color coded, what's shown here is just a demonstration of how supernova one parameter, while fixing every other parameter the same, what that might do to X-ray surface brightness. So I do not want you to read too much into where the median is, because that when you do the rule inference, you have to let all of the parameter free using this thing called Latin hypercube set. And then that there's a huge degeneracy, that no, the best fit model that's shown here is probably not coming from this blue one.
I see.
Yeah.
But then the main point is you need to have the maximum feedback energy to match the observed correlation.
It wasn't not necessarily maximum. It is higher than like in all of those cases, the best fit feedback parameters were generally higher, not maximum. You don't have to go all the way to
Okay.
the maximum so that we're kind of hitting the limit of what we're capable of
Okay.
exploring. It's actually less than maximum, but it is higher than the reference models in all of the TNG, SIMBA, Astra simulations. So that tends to indicate that regardless of the details of how you implement which models to use, the data seems to favor slightly more enhanced amount of feedback. That's all we could say.
I see. So I guess my main question is really from the observer side. It seems like there's also this question about star formation efficiency.
Yeah.
How much of that do you think that played into this underproduction of total stellar mass? Naturally, that's coupled with the amount of feedback as well, but it seems like they are not, while they are degenerate, but they are not completely coupled. Does that make sense?
That's right. That's an interesting question. And that, yes, they do have, I mean, the data, the ERAS data, I forget, I think which one we used out there. We have a one for star forming galaxy and we have one for quiescent galaxies. And we need we haven't really done this, but yeah, we don't have an answer to that questions as to what extent star formation rate is playing a role here. But that's an excellent question that there's a little bit more dimension to this analysis, which can be done, I believe, by looking at the data of quiescent and versus star-forming galaxies in different mass spins, and then there will, asking a question, what would that fit look like? This is the results of using all of it, but we didn't really dissect to what extent star formation rate is playing a role.
Yeah, understand. All right, Nastasha, quick question.
More a point to one of the things in terms of the coupling of feedback strength that you have in stars and CGM. I think there was I think it might have been from the Learning Universe or the SMOG team, the recent paper that had a motive that implemented like a high energy loading, lower mass loading mode of feedback that might have sort of a different ratio of effects on the galaxy itself and on the CGM. So that's sort of another slider that's maybe not within the current test, but there are potential ways within theory to affect the CGM more without messing up the galaxies as much.
That would be very interesting. Perhaps that this is an indication that such a parameter space has not maybe may not have been explored just yet in this particular set of simulation, but maybe the new model that has that different coupling of mass versus energy loading might help ameliorate the tension without having to fix the data. That would be very interesting if we can explore and come up with the because so far the models that we've looked at, which vary significantly still within, we were surprised, we're pleasantly surprised that we weren't able to find anything that could reconcile, but it would be interesting to come up with a model. What are the requirements of the model in order to, given the tension, how can we go about reducing that tension would be a very interesting question to ask. I hope that this kind of tension will drive more conversation and explorations in exploring different types of feedback model that might be able to then do something different.
Great. On that note, let's thank Daisuke again. And thank you all for joining us this time. I will see you next month, April 24th. The seminar will be given by Ben Oppenheimer, who is also on the online right now. But I look forward to seeing you all in a month. Thank you.
Thank you.
Thank you, Daisuke.